Okay, hello, welcome. Thank you. So please do sign in for the funding, and then we'll get started in like 30 seconds. And if you missed this or don't want to do it now, it's always on your handouts. So yeah. But okay, let's start. So chapter 14 is aromaticity. It's really easy, really simple, lovely, but it's also a little bit confusing. But there's just a few rules that you should know. And once you use those and can apply those to everything, you're pretty much set for this chapter. So, wait, am I unmuted? Yes. So, what do we know about aromaticity and stability? Yeah, it's stable. Is it more or less stable than a normal conjugated pi system? Yeah. So an aromatic system is more stable than a normal conjugated system. So when we have benzene, that's an aromatic system, right? And is that going to be more stable or less stable than what you'd expect from a normal unconjugated cyclohexatriene? Yeah, because it's aromatic. And then we rank in order of decreasing stability. So what comes first? Yeah. Then. And the worst one is, yeah. Cool. So let's fill in the rules for aromaticity. There's 4 criteria for a molecule to be aromatic. The first one is that it has to be cyclic. So no linear molecules. It also has to be planar. That gets a little confusing, but for the most part, just remember that anything smaller than 8 atoms is just automatically planar. And then the system has to be fully conjugated. So the ring has to be 2. Does anyone remember the things that we can have on a carbon make it sp2 hybridized? Yeah, an anion, cation, radical, and one more. Yeah, and a double bond. And then the last one, we need to have 4 n plus 2 pi electrons. And n can be any number. So if we just plug in any number, so we can start with 0, then we'd have 2. If we do 1, then we'd get 6. What's next? Like 10. Yeah, so on and so forth. And that's it. For it to be anti-aromatic, it's the exact same thing as aromatic, but instead of 4 n plus 2, we need to have 4 n pi electrons. So it's cyclic, planar, conjugated, and the difference is 4 n pi electrons. So it's going to be like 4, 8, 12, and whatever. And to be not aromatic or not anti-aromatic, all you have to do is just break one of the rules. So like if you have an sp3 carbon in the ring, or if you have like an odd number of radicals, because then you'll have an odd number of pi electrons, or if the molecule is like linear, that's all going to make it not aromatic or anti. Cool. So that's just for plain old carbons. But if we have a ring with a heteroatom in it, there's some more interesting stuff. So first for heteroatoms, they can sort of choose to be sp2 or sp3 hybridized. And then this gives them the choice to make the molecule either fully conjugated, allowing it to be aromatic or anti, or it can be sp3 and make it non-aromatic. If they choose to be sp2 hybridized in the ring, they can only donate one pair of electrons. So if you have an oxygen like this, it has two lone pairs. If this oxygen is in a ring, it can choose to become sp2 hybridized, but only one set of the lone pairs can be included because you can only have max 2 electrons in a pi orbital. So you would only have one set of these participating in the conjugated pi system. And it'll make more sense when we see examples of this. Okay, 2. If there's multiple single bonded heteroatoms in the ring, they must have the same hybridization. So for example, if we take this molecule, these oxygens are both attached to the ring by single bonds. And remember, heteroatoms can choose to be sp2 or sp3. So these oxygens can choose to be sp2 or sp3. But if they choose, they both pick the same option. You can't have one oxygen that chose to be sp2 and then another one that chose to be sp3. So if you have two heteroatoms in this scenario, when they're only attached by single bonds, they have to choose the exact same hybridization. So they're kind of synchronized. And then for double bonded heteroatoms, oh yeah. For double bonded heteroatoms, like we have in pyridine, they are always sp2 hybridized and they must donate one pi electron only. Okay, the fourth rule is that heteroatoms that are double bonded to the outside of the ring, like carbonyls, they act as cations in the pi system and contribute 0 electrons, like this. So I'll give you an example. We have this interesting molecule. It's like a cyclopropane with the ketone attached to it. What happens is that this ketone has a resonance form, like a Zwitter ion resonance form, where it basically looks like this. Over on this carbon, you have a positive charge, and on the oxygen, you have a negative charge. So because this is the resonance form, this carbon right here is going to be sp2 hybridized, but it's going to act as a cation. So all you need to know is that if you have something like this with a carbonyl that's bonded outside of the ring, the carbon that it's bonded to is going to donate 0 electrons, but it's still going to participate in the aromatic system. And the last one, boron is always sp2 hybridized, and it can't choose between sp2 or sp3, and it also donates 0 electrons. Okay, so if you didn't get a chance to scribble that down, you should take a picture so you can use it when we do practice problems. Okay, so there's this like MO diagram that just demonstrates why aromatic molecules are stable, but it's a waste of time, so we're going to skip it. And we'll go straight into this, which is much more useful. So we're basically just labeling each molecule as either aromatic, anti-aromatic, or non-aromatic. And you're going to use the 4 or however many rules I just told you to do that. So for the first one, what do we think? It's non because, yeah. So we have this carbon at the top, which is a CH2. This is sp3 hybridized, which breaks the pi system, so it's not fully conjugated. So it's just non-aromatic. We have these 2 pi orbitals at the bottom, but since this carbon at the top isn't a pi orbital or doesn't donate a pi orbital to participate, it's just silly and it's not conjugated. Okay, the next one. It's aromatic because it's cyclic, it's planar, smaller than 8 members. And how many pi electrons are there? Yeah, there's 2, 1 from each side of the double bond. So yeah, that's aromatic. All right, this other triangle. Yeah. Yeah, the positive charge. Remember, if we have a cation, anion, radical, or double bond on a carbon, it's sp2 hybridized. Okay, so triangle with a lone pair. What do we think? It's anti because there's 4 pi electrons. When we have a lone pair on a carbon, it's sp2 hybridized and the lone pair donates 2 pi electrons. So we have 2 from this double bond in the bottom and we have 2 from the lone pair on top. Okay, now we have an interesting one. We have a heteroatom. So, any thoughts? Is what? It should be anti, right? Because the oxygen has 2 lone pairs, but it only donates 1. So that should be 4 pi electrons. But heteroatoms can do what? Yeah. So they can choose to be sp2 or they can choose to become sp3 and break the conjugation. So if this oxygen chooses to be sp2, this molecule is anti-aromatic, right? And that's unstable. It sucks. We don't want that. So is oxygen going to choose to become non-aromatic? No? Why not? But if it's sp2, it's anti-aromatic because it's 4N. So it switches to non-aromatic, right? Okay, now we have a boron. Boron donates how many pi electrons? So how many are in the system? So it's aromatic? Yeah. And this ketone, which I just showed you. What do we think? It's aromatic? Yes, it is, because this carbonyl carbon acts as a cation, which would be sp2 hybridized. And because it acts as a cation, you only have 2 pi electrons in the system. So it is aromatic. All right, the square. It's anti because Okay, now we have a square with 2 dots. It's still anti because there's still 4 pi electrons. All right, square with a nitrogen in it. How many pi electrons are in the system? Yeah, there's 4, because remember the rule about double bonded heteroatoms. Double bonded heteroatoms in a ring only donate 1 pi electron. So you have 1, 2, 3, and 4. This lone pair is going to be sticking out horizontally from the molecule as its own orbital. It doesn't participate in the pi system. All right, we're on to pentagons. So remember the thing about the odd number of radicals? What does having an odd number of radicals make a molecule? Because we can't have 4n plus 2, and we can't have 4n either, because we have an odd number. So it has to be none. Okay, what about this one? There's how many pi electrons? So it's okay, this one. There's 6, so it's yeah. For this one? Okay, so we just draw one of these things on top of every sp2 hybridized carbon. And then if a carbon has a double bond on it, how many pi electrons? Yeah, 1 per carbon. So these all get 1, and this is a lone pair at the top. How many does that contribute? So we count up all the red dots and we get 6 pi electrons. It's just a thing we did for chapter 13, but less work. Okay. Okay, back to the heteroatoms. So how many pi electrons are in this? How many does the nitrogen give? Yeah, when nitrogen is single bonded to 3 things, it has a lone pair to stay neutral. So how many does that lone pair add to the system? So how many total? So it's, yeah. All right, this ketone thing. 5. There's 4. Because remember, this carbonyl carbon donates 0. So 4 pi electrons is anti. Okay, we got boron again. It's what? It's anti. It's the exact same thing as the ketone thing that we just did, because both the carbonyl carbon and the boron donate 0 pi electrons. Why are these all anti? We should have distributed this better. All right, this one. It's aromatic because there's and this thing. Sure, we'll give the oxygen 1, 2. So 6 pi electrons. Yeah, there's 6. So the carbocation gives you 0. The nitrogen, it's double bonded, so it gives you 1. The other half of the double bond also gives you 1. The oxygen could give you 2, or it could break the system, but we'll put 2 for now. And then the other 2 give 1 each. So we add up the red dots, that's 6 pi electrons, and that's aromatic. So the oxygen is going to choose to be sp2 hybridized, so it can be stabilized by the aromaticity. All right, this one. It's non. Yeah, because this is sp3 hybridized. Okay, so here's that example I drew earlier. So if the oxygens chose to be sp2 and complete the pi system, how many electrons would be floating around in it? Yeah, there would be 8. Is 8 aromatic or anti? So are the oxygens going to prefer to be sp2 or sp3? sp3, because it wants to be non-aromatic more than it wants to be anti. And then remember, if you have 2 heteroatoms in the same ring, they have to be the same hybridization. Like if they can choose, they're going to choose to be the same one. Okay, more ketones. What do we think? It's aromatic because there's 6 pi electrons. And what about that, but with a boron? Okay, we got this thing now. So how many lone pairs on the sulfur? 2. Because it's in the same row group, I don't know, as oxygen. So if both the sulfur and the oxygen choose to be sp2, how many pi electrons? Yeah. You have 2 from each and then 2 from the double bond, and then this is a cation. So if they choose to be sp2, it's going to be anti-aromatic. So do they choose that? Yeah, so it's non-aromatic. Okay, what about this thing? Yeah, it's 6, so it's aromatic. What is, yeah, this. It's also 8 because the lone pair has 2, so it's anti. Okay, we're almost done. Oh, so this is where it gets a little interesting. So, first I'll just let you do it. So what do you think? Is it what? Is it planar? So remember how the hetero atoms could choose to be sp2 or sp3? If you have a ring like an octagon, it can choose if it wants to be planar or not. So if it is aromatic, then it's gonna, or if it has the possibility to be aromatic, it's going to choose to stay planar. If it's going to be anti-aromatic in the planar form, then it just bends. So for this molecule, in its planar form, is it aromatic or anti? It's anti because there's 8 pi electrons. So it's anti-aromatic if it stays planar. But if you remember, there's like that boat, whatever conformation that cyclic molecules can go into. So it's going to do that. And that would make it what? That would make it non-aromatic. And it's going to bend to make itself non-aromatic because that's more stable than anti. Okay, the next one. That would be aromatic because you have 6 pi electrons. So is it going to stay planar or bend itself? Mm-hmm. Okay, now we have these bridged things. So what do we think about this one? It is aromatic. So how many total pi electrons are there? Yeah, so 2, 4, 6, 8, 10. And remember the carbonyls act as cations, so there's 0. 10 pi electrons is 4n plus 2, so that is aromatic. And then this thing, which is called naphthalene. Naphthalene? I don't know, how do you pronounce it? Mm-hmm. Yeah, also 10 pi electrons. God, how many are, okay. So yeah, we're nearing the end. Is this one aromatic or not? It's 10 because the oxygen is going to be sp2 hybridized and donate 1 lone pair. So 10. Almost. Huh? So if the oxygen chooses to be sp2, then it's aromatic, and since that's the highest stability, it's going to want to choose to like take that form. If it was sp2 and it became anti-aromatic, then it would want to become sp3 and break the system. So it would be more stable as non. Okay, almost last one. We have DAPA with boron. It's anti because there's 8 pi electrons and then the boron donates 0. Okay, now at the bottom, we have these things called annulenes, and I highly doubt that like Roche cares about them too much, but it's still good to know. So these are giant rings. So you're wondering if they're planar or not. I got really confused like trying to research if they're planar, because there's a ton of sources. There's a bunch of annulenes that like they're debating if they're planar or not, or they're aromatic, but yeah, whatever. It's not important. So for this one is definitely aromatic because the bond angle and the size allows the hydrogens to like coexist with each other in a planar form. So we can just draw on the hydrogens like this. And you see how there's not much steric hindrance. They all have their own space. So it can stay as a nice flat donut. So we know it can be planar. Now, how many pi electrons are in this thing? And is that aromatic? Yeah. So this one, how many pi electrons? There's 16. Is that 4n or 4n plus 2? 4n, so it's going to be anti. I don't think there's a more stable conformation for it to fold into, because when I was taking the class, they didn't tell me about it. So I don't know if it exists. But for now, we'll just say it's anti. Okay, cool, that's it. We can do chapter 13 practice problems now, unless you want more aromaticity. But I think we're all very clear about chapter 14. And I think that's basically it. Like, I don't know, on my exam for 14, I didn't have anything besides just like declaring stuff anti, non, or aromatic. So
it's just mostly the past chapter.
Huh?
The exams is mostly the past chapter.
Yeah, it's mostly 13 and 15. Okay, let me get my problems. Okay. Okay, so these are my chapter 13 problems from Dr. West, and they're pretty good, so we'll use them. So, correct. So this one, yeah, you can read the question.
Yeah.
But I didn't read it. Okay. High temperature, yeah, thermodynamic control. So it's thermodynamic because you have high temperatures and I don't know, it's allowed to like equilibrate. You sure? So we have Diels-Alder. We don't care about that massive explanation, and we also don't care about the starting molecule. It's just asking you to dimerize this diene. And by dimerize, we mean the diene reacts with itself. So who wants to react that with itself?
Oh, you said it with itself?
Yeah, so it acts as the diene and the dienophile.
This is basically like
Huh? Yeah, I did this exam.
Yeah. It's the black that works.
No, or the black, wait, is it? Wait, it should work.
Yeah.
I got a fresh pack of stickers for you all. Okay, I would rotate the dienophile to make your life easy. Yeah.
Oh, like
no, that works.
this
you
way,
s-
you usually one of them is.
Yeah,
Okay. Oh, yeah. So this one is this here, this goes here, this goes here.
hang on.
Oh, it's on
Yeah, that's right.
yeah, I'm gonna make it 3D after.
Please don't make it 3D. Yeah, no, just leave it.
Okay, so that one is basically. Wait, am I missing something?
I don't think so. Oh, the second half of the
Yeah.
molecule, yeah.
Let's get this one.
Just copy and paste whatever's on the right.
Yeah, and
Yes, that's perfect.
yeah. Okay.
So, sticker?
You okay?
I refreshed, yeah. So our final product, we just draw 2 bonds between our 2 squares. So our new bonds are gonna be this. Good, makes sense.
Where's the on the right side?
Well, it was always there.
Oh, and then I. Oh, that's actually cute. Formal.
I thought it was two, so it was like very quiet.
We could do one more of these, but I don't want to, so we'll just move on. So for a dial's Alder cycloaddition to take place, the most rapidly, what must the dienophile be? The dienophile. Yeah. So the first one. So to speed up the reaction, you attach electron withdrawing groups to dienophiles, and then what do you attach to dienes to make it faster? Yeah. Oh, there is a cool one. Yeah, number 28. Anyone want to do number 28? It's a 1-2-1-4 addition.
I know this question wrong.
Really? I'm sorry.
I am.
Isn't it just what? Yeah. But what are your products gonna look like? Yeah, it would literally just be 1-2-1-4. So my method for doing all of these is I label the dienes 1, 2, 3, 4, and then I attach the hydrogen on 1, and then I attach the halogen on 2 and 4, and there's your separate products. Congrats.
Every time?
Yeah. I have never come across an exception, but be careful.
For conjugated?
Yeah, for like a conjugated diene 1-2-1-4 addition. I mean, it's the name of the reaction. So your product's going to be 1, 2, and 1, 4. Oh, it's a D. Haha. And it's just asking for the products. So they're your products. Let's see. Okay, this one is interesting. So number 30.
Just like, there's one of the 5 bonds.
Yeah, they all just swing and bond with each other. So you draw your 3 arrows and then you draw your product. And I'm a little challenged with drawing these products, but I can do it.
It does make it back, or,
Yes. Oh, I messed that up. Damn. So I just replaced the pink arrows with new bonds, and that's all. Okay, these are stupid. These are stupid. Okay, so which of these 4 compounds is going to have the longest wavelength in UV vis spectroscopy?
The longest UV?
The longest wavelength, yeah. The bottom, yeah, the bottom left, because because you have all 4 double bonds conjugated with each other. They're all one single bond away. And the more conjugation you have, the higher wavelength you have and lower energy.
I was confused on the carbon, like the oxygen double bonds to the carbon. I thought we can only do carbon to double bond carbon.
No, any double bond.
I saw.
Yeah. What now? Okay, these are stupid. That's it? What?
Alright. So, not me.
Damn, I thought there would be more interesting ones in here. Ugh, now I have to go back. So number 18. Does anyone want to do number 18? Hmm? It is an alkyne.
I know what happened.
Please do. Oh, this is where my eraser is. Damn, I lost it for like 2 weeks. What functional group is that?
Carboxyl. No. Ester.
Ester.
Okay.
Wait. Oh, yeah. Thank you. Yep. Whoa, are you sure?
Maybe.
Are you sure it would be bridged? If it was bridged, how many carbons would the diene be? What?
2, right?
No, so what?
I was thinking flip up.
But we have nothing to flip up, right? It's just a square.
Oh, so fused.
Yeah, so like if we had that 2 carbon bridge head, then we'd have to have 2 extra carbons here, but they're nowhere to be found.
Kind of like how she. No, I'm sorry.
Where did the extra square come
I
from?
don't know. And then. Let's see.
You don't need to draw that.
Okay.
It's an alkyne.
Oh, yeah, sorry.
Yeah. Okay, great. Sticker? Yeah, sticker.
See, now I earned it.
Okay, so for this one, we took the diene, we did our 3 arrows, cool. So we have our 3 new bonds, and the dienophile was an alkyne. So in the final product, it turns into an alkene like this. And then we have that ester sticking out the side. And that's it. We don't have time to do any more, so that's all.